Porque é capaz de dar um bocado diferente. São muitas coisas diferentes, opções, mas isso tem que ser cuidado. As pessoas vão resolver esta questão. Como avaliar a condição das famílias?
Hello. Do you hear me in the room?
Basicamente,
sim, não sei. Sim.
Sim, a gente fala que você tem que estar privado, e já não estava muito. Não sei, acho que já tem que ser bem.
Não dava sempre bem, já estava cheio. Era um hotel, mas ali o vendedor. E o hotel como eu não sei. Estava cheio. Acho que estava assim. Mas já ganhava.
Sim, eu ganhava.
Eu tinha dormido, eu tive uma vida e eu ouvi, estava no igual.
Mas eu sei, eu ouvi.
Mas desligou em casa a festa.
Não sei se foi.
Eu já vi que aos momentos que eu olha, já estamos. Provavelmente eu comprei dois minutos.
Pois,
Eu não consigo.
bom dia. Bom dia.
Vocês viram no quarto?
Eu também não vi nada. Era baixinho. Aí fiquei pensando, agora vai ser o seu da minha mãe.
Tinha procurado um 09? Não.
Tinha assim, uma coisa.
Eu andava à procura de coisa vizinha.
Pois é que nós falamos que eu só estava já bem capa. Não faço o bico com ela. Eu acho que foi muito.
E agora vem a porta. Eu já ia lá para baixo.
Mais ou menos assim, mesmo.
Eu quero primeiro.
Sim.
Os computadores só não envio para o milhão confirmado. Fica. Trouxe uma lá, não queria. É o 14. Eu ia mandar as manhãs.
Hello, colleagues. Do you hear me in the room?
Agora só não vou.
Sim, mas também dá.
Does anybody here means room? No.
Mi pode ser adulto. Assim? Mas ormai não é presencial.
Não.
Eu tenho que ir ormai.
Ok.
Isso é melhor. A mim também dá jeito, até pode ser mais chique se quiser.
Eu também não. Tem que ver.
Mas para a população um bocadinho mais chique.
Depois dá para
Faz uma atividade um pouco. Então, a Paula, né? Sim.
Hello.
Sim, era o que estava mais. E não apontei que tinha as melhores.
É presencial, é falta.
Sim, sim. Não, eu tive um destino, tiveram aqui um destino porque acho que eu não vou bater. Mas depois. Descarta, eu não mandei. Eu disse que era descarta. E nunca cheguei a minha parte não consigo nada. É assim, tudo mais.
Sabe o que não sai? Não chatei.
Não vou te dizer.
O problema deles é que conseguiram mudar no mundo. Então, se não, as pessoas que ficam, não dá para ir. A única coisa que eu tenho que assim, não está a dizer que não está bem, não está a contar.
Você não tem nenhuma. É que os assuntos eu também não sei se você não ouviu.
A ideia já está.
Isto já vai ser. Já estou com uma
Não, mas eu vou isto mas ao menos
mas perto do não é. Então,
não.
e perto do acesso a esse não.
Mas depois.
Vai ter que jogar, né? Estes nós ainda vai ter que jogar.
Deve ser mais dos três.
Sim.
Se calhar é melhor não.
Ela vai estar de maneira institucional, mas pode muito bom. Mas quem tivesse sido bom,
Allora,
Ok, Maxim è collegato, tutto funziona. Qui in questa stanza non funziona la webcam, quindi non si può vedere. E adesso c'è una presentazione in presenza, giusto?
Sì.
Ok, allora che sarebbe questa, giusto?
Sì.
Ok. Adesso la condividiamo. E
Sì, chiudi un po'. Ok, quindi poi farò lo stesso per l'altra.
sono due in presenza.
No, ah no, scusami, gli altri fanno da soli.
Devi fare solo stop sharing quando. E gli altri, poi non devi toccare niente perché gli altri fanno da soli e devi premere solo su Chrome per vedere cosa stanno facendo. Ma comunque, se questa è la prima presentazione, io adesso vado a presentare di là e poi ritorno di qua.
Sì. No, l'importante è che era già connesso, non sapevo.
Sì, 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 cioè, lo fanno già loro.
Ah, ok.
C'è Maxim che è presente. Ok.
Sì, sì.
Grazie.
Sì, ovviamente mi piace necessario.
You are the first one? To be.
Se não quiser voltar pro pessoal, pode tirar um e-mail com a mesma instrução. Eu já fiz isso. Exatamente igual, só pega e-mail. Se isso faz a investigação da.
É verdade. Só depois, se não faz o encaminhamento e não vai lá depois, não vai.
Sim, sim.
Eu também tenho um e-mail, uma vez que eu decidi, eu consigo encaminhar entre esse
Good morning to everybody, and welcome to this session. The first speaker is Professor Ricardo Coelho. He talks about Bayesian models to predict above ground biomass. Please.
Thank you for the presentation. Hello, my name is Ricardo Coelho, and I am a PhD student. My work is Bayesian models to predict the above ground biomass. This work is supervised by Professor Isabel Natário and Sylvia Freck. Okay, this is a summary of my presentation. Estimating the amount of carbon in forest is important for understanding the climate change and helping with the emerging carbon credits markets. The carbon can be quantified through above ground biomass, since we have the following relationship, and the AGB can be estimation using direct or indirect methods. The first one involves the destruction of the trees, while the former don't. Okay. With indirect methods, we have allometric equations, where these methods are functions of the characteristics of the trees. An alternative, we have the remote sensing, where in the last years, the remote sensing data have been used to estimate the AGB, where these data have been combined with the forest inventory data. In the last years, many machine learning models have been applied to estimate the AGB, because these models are flexible, and these models are assume fewer assumptions. However, some machine learning models don't account the special autocorrelation or the uncertainty. To solve the uncertainty, we can use the Bayesian approach, and to solve the special autocorrelations, we can use the hybrid models. The hybrid models are are models that combine statistical models with the machine learning models. Okay, the aim of this study is estimate the AGB in params, where these regions belong to Spain. For this, I use two Bayesian machine learning models, one hybrid models, and one statistical model, where this model is the Bayesian geostatistical models. Okay, in this study, I consider three data sets. The first data set is the inventory data from the 4 national forest inventory. The second data set is the satellite data from the satellite GeoSat-2, where this satellite belongs to the company GeoSat. In addition, I use the forest map of Spain to select the stadiles within the forest areas. In this figure we have an stadile where the stadile is characterized by your center, and your radius is 25 meters. Okay, from the inventory data, I use the allometric equations to compute the AGB for each tree. Then the response variable is the AGB, where the response variable is the sum of the AGB of all trees in each stage. Using the Kolmogorov-Smirnov test, we can assume that the response variable follow a normal distribution, since we have the p-value is greater than 10%. Okay, was covariates. Was covariates from the satellite. I use 4 reflectance bands, 4 vegetation indices, and 1 variables of the texture, that is the homogeneity. In addition to these covariates, I use 3 topographic covariates that are altitude, slope, and expect. Okay, in this figure, we have the Spearman correlations, where we can see that there are high correlations values. To solve the multicollinearity problems, I use the VIF method. The VIF method is the variance inflection factor. Okay, after I use this method, the covariates retained are the reflectance band blue, the vegetation indices NDVI and GCI, and the texture homogeneity, and the 3 topographic covariates. In addition, I consider the covariate the forest type. Okay, in this figure, we have the empirical residual semivirograms, where in this figure we have some models to fit to the empirical semivirogram. From this figure, we can conclude that the model Matern is the best model that fits to the empirical semivirogram. And in this figure, we can see the empirical variogram with Monte Carlo envelopes. From this figure, we can assume that there are residual special autocorrelations because there are some points without the envelopes. Well, okay, the first method is the statistical model, where this model is the Bayesian geostatistical model. In these models, we have the fixed effects and one special random effect, where the special random effect is modeled was a Gaussian field with matter covariance. This model is fitted using the package RIM in software R. Okay. The first machine learning model is the Bayesian additive regression tree. Okay, in these models, the response variable assume the distributions, and this model is very similar to the random forest, but in this case, in the Bayesian additive regression tree, the parameters of the random forest assume prior distributions. Okay, in this this model is fitted using the BART machine, the package in software R, to select the number of the trees, the value m. I use the cross validations, where in this case the m is equal to 50. Yeah. The hybrid model that I consider is a combination between the BART model and the geostatistical models. This model, in the first one, I fit the BART model to the data, and then I compute the residuals. From the residuals, I use the Bayesian geostatistical model to predict residuals. The final predictions are combinations between the predictions from the BART model with the predictions from the Bayesian geostatistical model. In these models, the predictions of the uncertainty is obtained by combination the posterior samples from both models. Okay. Okay. The last machine learning models that I consider is the BART model. This model. In this model, unlike the hybrid BART, we can see this model was a joint model, where the BART model and the spatial component are modeled simultaneously. Okay, to fit these models, I use the BART-Sim package of the software R. Okay, in this case, the number of the trees is the same of the model BART and the hybrid BART. Okay, in addition, the partial dependence plots are used to interpret the covariate effects in the BART and the BART-Sim models. Okay, to compare the models, I use the spatial block cross validations with 5 folds. I use these methods to account the spatial autocorrelations and the metrics, and to compare the models. I use the following metrics: the root mean square error, mean absolute error, to evaluate the predictions accuracy, to evaluate the goodness of fit. I use this metric, and to evaluate the uncertainty, I use the coverage prediction interval. Okay, the results. In these tables, we have the results of the four models. We can conclude that the geostatistical Bayesian model is the best, is the model that have the best predictive performance in the metric RMS. Okay, root mean square error, mean absolute error, and this metric, and the hybrid BART is the best model that quantify the uncertainty because this value is very close to 95%. Okay. Okay. In this figure, we have okay. In this slide, we have two figures. In the first figure, in the figure of the top, we have the predictions maps where in these maps not there are difference, but in the second map, in these maps, we can see some difference. Okay, in this map is the special the special is the special is the correspond the special effect where where we can see some difference in terms of the intensity of the special pattern. Okay. Okay. In these slides, in these slides we have some results from the statistical model where we can see that the topographic covariate aspect and the vegetation index GCI and the forest type are statistically significant at 5% level. In addition, the covariate aspect and the GCI are positively associated with the HB since the parameter is positive, and the forest type show lower IGB compared with the coniferous forests. Okay, in this figure we have the partial dependence plots, where this figure corresponds the BART models, and in this figure corresponds the BART-SIM models. Okay, in this figure we can see that, for example, in the covariate blue, where the covariate blue increase, the mean of the predictions of the response variable decrease. The same can be observed in the BART-SIM models. Yeah, in these these figures are very similar. For example, in the covariate NDVI, when the values these covariates increase, the mean of the response variables was increased. Okay. Finally, some conclusions. In these works, we can conclude that the best models, the best model is the statistical models, Bayesian statistical models. This model is the best in terms of the punctual predictions, but in terms of the uncertainty quantifications, the best model is the hybrid BART. aggregate methods. Yeah, and some references. And thank you.
Thank you very much for your talk. Are there questions? Remarks? If not, let's thank again the speaker. The next speakers will be online.
Hello, do you hear me?
Professor Protasov. So,
Yes,
can
do
you
you
hear
hear me? Do you hear me?
we
Hello.
don't hear you.
How can I share? Hello. Maybe you should turn on something.
We don't hear nothing.
My microphone. Is on. So, do you hear me?
Also here it's on the speakers. Please wait a moment for the technical assistant in the room.
Okay.
No.
Hello?
Hello. Do you hear me?
Yes, Maxim, I can hear you.
Good.
Okay.
How can I start?
But I don't know
for a technical assistant because all things are working here, but we don't hear your voice.
Yeah, but somebody is hear me.
We see your screen.
I am on the meeting, I can hear you, but I don't know why they can't hear you. Maybe they have an issue. For me, I can hear you.
Maybe you should maybe in the room you should.
She called
Hello.
someone, maybe for her.
Hello.
Allora, sai che facciamo? Chiudiamo? No, non posso
Sì.
chiudere.
Prova a chiedere se ha risolto, perché loro dicono che il microfono è acceso.
Maxim.
Yes,
Maxim.
yes. Do you hear me?
Ah, ma non sta accadendo questo.
Ah,
Maxim.
Do you hear me now? Hello.
Maxim.
Yes, yes, I hear you.
Do you hear
Do you
me?
hear? Yes, I hear you.
Maxim.
Yes, I hear
C'era un
you.
altro? Chi sta condividendo? No, Maxim. Maxim.
I hear you.
Tell her in the chat that you hear her.
ho anche provato ad alzare il tiro.
Illustrazioni audio, microfoni, ok.
Seduto proprio, letto parlare. Mi sembra che non sentiamo.
Maxim, mi senti? Ah, sono loro che non sentono noi.
No, siamo noi.
Ah, ho capito.
Però si sente mica qui. Quasi proprio strassi.
Do you hear me now?
Okay.
Sì,
Okay.
yes.
Yes. Now.
Thank
Yes.
you.
Oh, very
Thank
good.
you.
Do you see my screen? The full screen?
Yes, but also half. Your
Half?
Yes.
Sorry. One moment. Let me try.
Okay.
One moment.
Yes. Yes.
Let me do like this. Do you see it now? Is it good?
Yes, it's okay.
Okay. So
So
may
the
I start?
yes, the second speaker is Professor Protasov, and he talks about beam forming and supergrounding for the seismic data enchantment in the 5D domain. Please, Professor.
Okay. Thank you very much. Good day, ladies and gentlemen. My name is Maxim Protasov, and you already hear the name of my talk. So let me come like this. This is content of my presentation, and first I will briefly present the motivations, then I start with the trace statistic analysis, and then I will come to supergrouping and beamforming as a 5D data enhancement method, and then I will present numerical investigation of the proposed method on synthetic data, and finally I describe on real data application, and I will finalize with the conclusions. So, modern land seismic data are typically acquired using high spatial trace density with small source and receiver arrays or point sources and sensors. These datasets are challenging to process due to their massive size and relatively low signal-to-noise ratio caused by scattered near-surface noise. So, when pre-stack data enhancement becomes a critical step in the processing flow. And nonlinear beamforming was proven very powerful for 3D land data, as you can see on this slide. But from one side, it requires computationally intense estimation and summation in 3D pre-stack data cubes. And from another side, it operates in 3D domain, while seismic data have 5 domains. Therefore, we provide future development of computationally efficient seismic data enhancement taking into account 5D nature of seismic data. So let me now come to, I will explain the difference when operating in 3D and 5D domains using trace statistic analysis. And here, our analysis examines trace number statistic for typical single sensor real data geometry that you can see on this slide. And the acquisition parameters here are as follows. Source grid spacing in x direction is 75 meters. in Y direction is 12.5 meters. Receiver grid spacing is 12.5 meters in X direction and 150 meters in Y direction. So while conventional seismic data contains 4 spatial dimensions, the individual techniques each utilize only 2 spatial coordinates plus a time coordinate. In our terminology, 4D geometry employs all 4 coordinates, and 2D geometry fixes 2 coordinates. For example, here it's XR and YS, while varying the remaining 2 XR and YS. So the data enhancement procedure can implement in 2 distinct approaches. 2D case varying only 2 coordinates within the aperture, and this is the implementation used in developed procedures of beamforming and supergrouping. And for D case, varying all 4 coordinates within the aperture. And we have computed and compared the number of traces within the aperture for both cases, examining how these values scales with aperture size. And the K observation includes, for example, here in 4D approach, 1,000 tracings require 125 meter aperture. 10,000 traces require 150 meter aperture. And 600 meter aperture yields 1 million traces. But in 2D approach, 1,000 traces requires 200 meter aperture, and 10,000 traces requires 600 meter aperture. And so our trace statistic analysis demonstrates that the 4D spatial domain provides substantially more traces over 10-fold within a given aperture compared to the 2D spatial domain. These findings strongly support the superiority of the 5D approach, which incorporates all 4 spatial coordinates, source and receiver plus time for seismic data enhancement application. And therefore, the 5D methodology offers 2 key advantages: potential for significantly higher signal-to-noise ratio because of more traces, and more comprehensive utilization of available seismic information. Therefore, we come to modification of our supergrouping and beamforming approaches. And to fully realize these benefits, we have developed an innovation solutions that combines both of these techniques in a manner that effectively accounts for all 4 spatial coordinates. And from a technical perspective, 5D data enhancement can be effectively achieved through the implementation of supergathers. A supergather is created by combining several common depth point gathers into a single, more comprehensive gather. And so in our research, we have thoroughly investigated the most suitable data domains for the combined application of supergrouping and beamforming, presented several viable options. One primary configuration utilizes the cross-spread domain for beamforming operation, while employing its orthogonal counterpart for supergrouping. With the beamforming procedure in the cross-spread domain, we consider a second-order travel time approximation that you can see here in the 2D plane. And however, working with the CDP gather or supergather composed of multiple CDPs, the trace points XRYS within such gather are neither identical to each other or equal to the parameter trace. So, and this observation implies that 2D approximation is incomplete for this scenario and should instead be considered in a 4D plane, and thereby evaluating the data enhancement process from 3D to 5D. And to address this, we introduce the missing term approximation that you can see here. And Implementing this complete real-time approximation require estimating 9 additional parameters that is presented here, which demand substantial computational resources. Alternatively, we can apply beamforming in a context and examine its application for the complete real-time approximation in the 5D domain. And this approach effectively reduces approximation back to 2D approximation, implying that the additional parameters are set to 0. And this reduction means we perform summation in the orthogonal plane using a horizontally flat approximation. When we consider how supergrouping operates, we recognize that implicitly performs this operation in the orthogonal plane. And therefore, applying beamforming to supergather consists of two components: beamforming in the cross-spread domain and supergrouping in the domain orthogonal to supergather. Recognizing that supergrouping is inherently less precise than beamforming and is best suited for small apertures, we must consider alternative, more suitable operating domains for supergrouping. For supergather created from the nearest CDP gathers, the CDP domain emerges as the optimal choice for supergrouping due to the naturally small apertures resulting from the supergather construction. This domain offers an additional advantage for horizontally layered geology, as the geological context perfectly justifies setting the additional parameters to 0. To demonstrate this mathematically, let us examine 5D enhancement in the CDP offset domain, defined by the following coordinates. So this is CDP coordinates, this is offset coordinates. And so coming to these coordinates, analogous to previous approach, we consider a second order travel time approximation in the 2D domain. This is will be 2D approach. And expanding this with the missing terms yield complete for D approximation. And in this case, when the additional parameters are set to 0, it means we perform summation in CDP plane using a horizontally flat approximation. Since the supergather is constructed from the nearest CDPs, this domain is particularly well suited for supergrouping. Considering the geological context of the Arabian Plate, where reflections are predominantly flat, this domain becomes an ideal candidate. And therefore, we also provide the option of this approach, 5D data enhancement in CDP offset domain. So now I will show the numerical results investigation on synthetic datasets. So this is, as mentioned above, 5D data enhancement can be effectively achieved through the implementation of supergathers. And here, a supergather is, as I said, a supergather is created by combining several common depth points gathers into a single, more comprehensive gather. Here is presented examples of such gathers. And then, in order to provide a feasibility study of the proposed and approach, we create 3D synthetic data for realistic 3D acquisition geometry. From that data, we have created one central CDP gathers and 3 super gathers consisting of 3x3 CDP gathers, 5x5 CDP gathers, and 7x7. At the end, we add additive Gaussian noise with different level, coming to 100% noise. And next, we start testing the developed code on the created data set. So we choose rather small apertures for testing equals to 50 meters. And
You have to connect.
do you hear me?
The screen in the room.
Excuse me, do you hear me? Excuse me?
No.
You don't hear me again? Hello. So you don't hear me again, right? I don't hear you now. Сломалось. Мгм. Do you hear me?
Yes.
Yes, we hear you.
Where should I start from? Which slide should I start?
Number 10.
Number 10?
Maybe number 10.
Yes.
Okay.
Sorry,
Let me
sorry for
come
this
back.
situation.
Let me come back to number 10. So as I said, so the supergrouping and beamforming 5D approach can be realized not only in cross-spread domain, but also in CDP offset domain. And these CDP coordinates and offset coordinates. So we come from source receiver coordinates to CDP and offset coordinates. And then the approximation, travel time approximation, can be created in these domains. And so analogously to previous approach, we consider a second order travel time approximation in the 2D plane and expanding this with the missing terms yield complete approximation in 4D domain. So do you hear me?
Yes, yes.
Yes.
Okay, I can continue, right?
Yes.
So, okay. So again, in this case, when the additional parameters that we introduce, it means we can set them to 0, and it means that we perform summation in the CDP plane using a horizontally flat approximation. This is key point, and since the supergather is constructed from the nearest CDP points, this domain is particularly well suited for the supergrouping. And considering the, moreover, considering the geological context of the Arabian plain, where reflectors are predominantly flat, this domain becomes an ideal candidate. And therefore, we also provide the option, this option of 5D data enhancement in CDP offset domain. And now I can come to the numerical investigation on synthetic dataset. So as I mentioned above, 5D data enhancement can be effectively achieved through the implementation of supergathers. And as I said, supergather is created by combining several common depth points, gathers into a single. And here are presented the examples how we combine these supergathers. And then, in order to provide a feasibility study of the proposed approach, we create a 3D synthetic data set using realistic 3D acquisition geometry. And from that data, we have created several CDP gathers, super gathers, combining from 1 CDP, 3 CDP gathers, and 5 by 5 and 7 by 7. And also we provide additive Gaussian noise. And next we test the developed code, and we use rather small apertures. What is important that in this case we coming to 5D data enhancement, we can use small apertures. This is the main feature of this approach, and here we use 150 meters. And so we apply the approach with different noise level and different number of gathers in cross-spread domain first. And on this slide, visual inspection clearly demonstrates an improvement in data quality when comparing the enhanced data to the original noise input data. And additionally, the visual analysis reveals that the quality of noise reduction improves as the number of gathers with each super gather increase. So this relationship holds true for both the cross-spread and offset domains also. And it also visually apparent that for particular noise data sets, a greater number of gathers per super gather is required to achieve satisfactory enhancement results, again applying equally to both domains. However, the visual observation only provide qualitative enhancement. So to make more precise comparison, especially in case where visual differentiation is challenging, we conducted a quantitative analysis by computing correlation coefficient between the ideal data that we know from our synthetic data and the enhanced data obtained under various conditions. And these conditions included different domains, varying noise levels, and different number of gathers per super gather. And the resulting correlation coefficients that you can see on this table not only confirm our visual observation, but also establish the maximum achievable enhancement values, those obtained with the noise-free input data, as you can see. So the table reveals several important findings. So first, for smaller super gather configuration, specifically 1 gather and 3 by 3 gathers, the cross-spread domain yields the best achievable result. However, for larger configurations, 5 by 5 and 7 by 7 gathers, the offset domain produce superior outcomes. And this pattern persists when processing noisy data, with one crucial exception. When noise level becomes excessive, smaller super gather configurations provide proof inadequate, resulting in acceptably low correlation coefficient. In such cases, larger super gathers become necessary to achieve proper enhancement. And furthermore, when working with significantly noisy data, the offset domain, which is new option of the 5D data enhancement, should be selected to obtain optimal results. And these empirical findings align perfectly with the theoretical framework that I described earlier. So also, additionally, we compared computational times across the various scenarios described above, and the complete set of computational times for different scenarios is presented in this table. Particular importance is the comparison between optimized 5D enhancement and not optimized processing. The result demonstrates that the optimization provides computational acceleration of the summation process by a factor from 2 to 7, and depending on the operation domain, number of OMP threads, and the number of CDPs in the super gather. Another noteworthy observation is that when using the optimization, computational times become similar between the offset and cross-spread domain. And this is also benefit of the provided offset domain. So, and finally, I present the test results obtained from real seismic data acquired in the Arabian Plate. And the data set contains numerous different types of noise, making it particularly challenging to identify and trace reflected wave events. We have applied the developed 5D data enhancement methodology to process various supergather configuration across different domains. Here is presented result of the 5D data enhancement in CDP offset domain with CDP apertures equals to 25 meters. Here on the right, this is the result. And then here is presented result in CDP offset domain with the apertures equals to 125 meters. And in general terms, these real data results provide clear confirmation of the conclusions we previously drew from the synthetic datasets. More specifically, we have demonstrated significant improvement in signal-to-noise ratio through the application of the 5D data enhancement, even when using relatively small apertures in CDP supergrouping domain. This result strongly indicates the considerable potential of our proposed approach for enhancement of data quality. And now, finally, I come to the conclusions, where I have to say that we have developed a novel seismic data enhancement approach along with its corresponding software implementation that enables comprehensive processing of data in the 5D domain. And this innovative methodology combines two powerful techniques, seismic data supergrouping and nonlinear beamforming. By integrating these complementary techniques, we have created a robust solution that effectively accounts for all four spatial coordinates simultaneously. And so our research has systematically investigated the most suitable data domains for optimal performance when applying supergrouping and beamforming in combination. And based on the comprehensive result, we conclusively demonstrate that our developed approach represents a significant advancement in seismic data processing, and this new 5D data enhancement tool successfully handles all spatial data coordinates while consistently delivering the best achievable processing result under various conditions. And I have to say that after I'm grateful to Saudi Aramco for the support and for the permission to publish the result. And also this work is partially supported by the Russian Sound Foundation. And thank you for your attention. And if you have any questions, I will try to answer them.
Thank you. Are there questions? Remarks only from the audience in online? Okay, if not, let's thanks again the speaker.
Thank you.
Thank you. Thank you. And we are ready to pass to the next speaker. Are you online? The next speaker is online.
Please, Ali Idri.
You can share your screen.
Okay. We can see the presentation?
Yes.
Okay. Okay. So hello everyone. Sorry?
Please. The floor is yours. Yes, you can speak.
Okay, thank you. So hello everyone. Today I'm going to present our work, me and the professor Ali Idri. So I am a PhD student at INSEAD in the Mohammed V University in Rabat, and our work is titled Evaluation of Filter and Wrapper Feature Selection Methods in Species Distribution Modeling. Okay, so I'm going to start by an outline. So we're going to start by an introduction. Then we're going to move to the material and methods used in the study. Then we're going to move to the experience where we detail the steps used in this work. And we will move to results and discussion. And finally, we will end our work by conclusion and perspectives. So, biodiversity conservation has become one of the most important global challenges, as biodiversity plays a fundamental role in maintaining ecosystem and supporting life on Earth. However, the continuous decline in biodiversity has the potential to disrupt ecological balance, and this make the protection of species increasingly critical. So to address this challenge, ecologists have developed many methods to better understand and predict species distribution. Among these, species distribution modeling or ecological niche modeling or simply SDM has become one of the most widely used tools. So, as a motivation, maintaining biodiversity relies heavily on safeguarding and conserving diverse species, especially birds, because in our work we're going to talk about birds, their habitats and ecosystems. And the disappearance of one species can threaten the survival of others, even human beings, because they are considered species. And feature selection has a considerable impact on increasing the model performances by including the ability to reduce the number of measurements or features and decreasing the execution time. So the main significant contribution of this work is to compare the performance of 4 classifiers using 6 univariate filters with 40% and 50% thresholds of the main data sets, 2 multivariate filters, 6 wrapper methods, using 7 bird data sets with 2 groups, the Phoenicurus group, Misheri, Phoenicurus, and Oculus, and the Onenth group, which contains Leucopiga, Deserti, Onent, and Leucura. Using the Scott-Knott clustering test, it is a statistical test, and border count method to assess and contrast how feature selection affects classifier performance. So in total, our work evaluates 588 variants of test setups, 4 classifiers, times 6 univariate filters, times, 2 thresholds, 2 multivariate filters, 6 wrappers, and the original feature set over 7 data sets, and which aims at addressing the following research question: how do filter and wrapper feature selection techniques compare in terms of accuracy, kappa, and F1 score. So as you see, we are focusing on Morocco, and we used, as we mentioned, 7 data sets, 3 red-start birds, Phoenicurus misheri. They have a common name, misheri is the red-start. Also, the scientific name of the second species or category is Phoenicurus oculus. They are called black red-start. And Phoenicurus, they are called camel red-start. And we have 4 wheat-eared birds, Onent deserti, Onent leucopiga, Onent leucura, and Onent. For the environmental data, we have 20 environmental data, and each climate has a definition. So the climate one or the feature one represent the annual mean temperature. The second climate, the mean annual range. The third one is isothermally or isothermality. The fourth one is temperature seasonality. The fifth one is maximum temperature of the warmest month, minimum temperature of the coldest month, temperature annual range, mean temperature of the wettest quarter, mean temperature of the driest quarter, mean temperature of warmest quarter, mean temperature of coldest quarter, annual precipitation, precipitation of wettest month, precipitation of driest month, precipitation seasonality, precipitation of wettest quarter, precipitation of driest quarter, precipitation of warmest quarter, and we have precipitation of coldest quarter, and finally elevation. And this information is collected from the worldclimate.org website. So these are the environmental predictors used to model the distribution of the 7 bird species. So in our work, we used 5 cross-validation method to avoid overfitting. We used for model measurements, we used accuracy, F1 score, and kappa. We used as a statistical tool the ESCA test, as it is known the best one for now, is a clustering algorithm commonly used in the ANOVA of variance. It is based on clusters, and the best cluster is the one that we use to apply the border count, which is a ranking method or a voting method for a single winner. But the border count, it is based on all the metrics you used. However, the ESCA test, it is based on accuracy. And in each group, we have the models that have the same predictive capabilities in terms of accuracy. Here, as you see, we have the 7 data sets. And for the steps we used is for each data set, we generate a feature subset using 6 univariate filters with 40% and 50% thresholds, 2 multivariate methods, 6 wrapper methods. So this results in 20 variants per data set. So 20 times 7 data sets is 140 data set variants. Then we have used 4 classifiers, DT, LGBM, XGBoost, and Random Forest. We trained them on each feature subset generated in step 1, as well as the entire or the original feature set. And we applied 5 47 to compute accuracy, kappa, and F1 score. So in total, we have 147 model variants per classifier across all datasets. And the performance of filter and wrapper methods, since in this work we are trying to compare between them, was compared using the ESCA test and the border count to determine statistically significant differences and overall rankings among methods. So here in this table, we are presenting the proportion of wrapper and filter in the ESCA test. How often do the wrapper methods and filter methods appear in the best ESCA cluster? So since we have 6 wrappers and we have 4 classifiers, so 6 times 4 is 24. So in total we have 24 combination of wrappers, and these wrappers for example, the first data sets appear 13 times over 24 in the best ESCA cluster, which represents 54.70%. For filters, we have 36.67%. So the wrappers dominates, or we can say that the wrapper methods perform better than filters for this dataset. For the second one, we can see that the filters are a little bit higher in terms of percentage, but we can say that they are similarly performing the same. For the third one, we can see that the wrapper methods are preferable. For this one, they are similarly performing equally or the same. For this data set, the wrapper are best. For the 2 remaining ones, also the wrapper methods are best. So we can say in overall that the wrapper methods based on the ESCA tests are performing the best. So in terms of performance. Here we see the occurrence rates and the border count of the feature selection methods in the top clusters of the 7 datasets. So instead of seeing each data set separately, we are seeing globally what are the wrappers and filters that are performing the best. So for the Borita wrapper, we have 19 times out of 28. 28 because we have 7 times 4, 6 wrappers plus the original feature set and 4 classifiers. So they are appearing 19 times out of 28 in the best ESCA cluster, and they were ranked first 3 times, fifth, fifth, eighth ranks 1 time. They appeared in the sixth rank twice. The consistency, which is multivariate methods, appeared 18 times out of 28, and its fifth rank appeared 4 times, so it was 4 times ranked fifth and 1 time ranked sixth. So we classify them by the occurrence rate, then the board account ranking. So for now, we can see that the Borita is the best one, and it is a wrapper. Then we have consistency, which is a filter, genetic algorithm, which is a wrapper, recursive feature elimination, which is a wrapper, sequential feature selection, which is a wrapper, permutation importance, which is a wrapper, and supply, which is also a wrapper. So we can see that the wrappers are still dominating, which also support the finding of the previous slide. This is the continuation of the rankings. Here we use the board account. So all the methods you see here are the methods that appear in the best ESCA cluster. And these methods were ranked based on the 3 performance metrics. We can see that the best one is sequential feature selection with random forest. However, in this study, we select the best method with fewer number of features. Since all these methods have the same predictive capabilities because they are appeared in the same best ESCA cluster, we can see the one with the fewest number of features. So here we have for filters ANOVA with 40% and genetic algorithm with 7 features. For Acros, we have SFS, and for the features, we have Fisher score. Here we have SFS and mutual information, permutation important and t-test, permutation important and SFS. SFS and Fisher score, SFS and Fisher score. So generally, we can see that the SFS, which is a wrapper, and Fisher score are the best feature selection techniques in terms of number of features and performance. Here is the median values. So here is the ESCA test, but for all the 7 datasets. So we can see that the best one is for SFS, original, permutation importance, recursive feature elimination. However, these methods were trained respectively with 10, 21 features, 10 features, and 14 features. So the best one with the fewest number of features is SFS. And we can see that also based on the board account, SFS appeared. And in the occurrence rate, the SFS appeared the 5th one. And in this slide, we see that the wrapper methods are the best. So we can see, as a conclusion, that the SFS achieves the highest overall performance. However, considering feature reduction, Fisher score combined with random forest was the best choice because it selects in average 9 features instead of 10. So as a perspective, we aim to compare the performances of additional filters and wrappers using more datasets, build ensemble feature ranking methods by using additional feature ranking techniques for promising results, employ interpretability techniques to evaluate the trade-off between predictive performance, and compare the global and local interpretability techniques. So thank you so much for your attention. And if you have any question, you're welcome.
Thank you, Professor Sherif. Are there questions? Question? Max. So, thank you again.
You're very welcome. Thank you so much.
Okay, we can pass to the next speaker. It's here. Professors Abuzelezi. I didn't see the other speaker. I don't see the other speaker. Okay, so I think that this session is finished because I don't see other speakers present online. Last end?
The last one.
Last one, but also another one in the middle. See, yes, it's not present. Okay, so thank you very much for all speakers of this session, and we have a break now. Thank you.
Thank you. Goodbye.
Thank you. Goodbye.
Bye. Bye.